In this video, let us try to understand what is power characterization, and in that we are dealing with static power. And in the next videos, we will be seeing about dynamic power. Here, if you see, power has played an important role in our recent electronic devices like iPhones, iPads, or any electronic gadgets that you pick up. It has something to do with power. We have to store power, and whenever we talk about all these electronic gadgets, where we have all these millions of transistors switching inside the electronic gadget. So we need to control the amount of power that is being consumed by each and every transistor, and for that we need to model the power in such a fashion that is understandable by the designer, so that they can design and control the power supply so that all the devices will consume less amount of power. We have different kinds of powers like static power and dynamic power. So switching power comes under dynamic power. Let us see all these things in more detail. And here remember this one note. These leakage currents will be multiplied with the supply voltage to get power. So we know that the formula for power is equal to V into I. So therefore this leakage power should be multiplied with the supply voltage to get the power. First one, let us see what is static power. So static power is also called as leakage power. The term power and current are used interchangeably. If we make use of these terms called as current, we can reduce real analysis as well as power analysis. So we use these two terms interchangeably whenever required. There are different kinds of leakage powers and they are classified into three types. In that, let us see first one, that is called as subthreshold current. So let us see what is meant by subthreshold current. The term itself tells us that it is something that goes below the threshold voltage of the transistor. We know that threshold voltage means it is the minimum amount of voltage across the gate terminal to form a channel. Let us try to understand with respect to NMOS. So here I am taking N, this is P and this is N. You can call this as NMOS, where here source and body are connected to ground, and we need to apply the potential between gate and source for the formation of channel, and for the flow of electrons we need to apply potential between source and drain. When we apply positive potential at gate terminal, the majority carriers, which are holes in the P substrate, move downward and it leads to the formation of the channel. So the minimum amount of voltage that should be applied across the gate terminal for the formation of channel is called as threshold voltage. And when VDS is greater than 0, the majority carriers, which are electrons, start moving from source to drain, because of which IDS current will flow from drain to source. Let us see what does this mean. So here P, which is positive, so I am connecting gate to positive and source to negative. This is positive, this is negative. So because of this, it leads to the formation of channel. So here channel gets formed, and we need to apply the potential between drain and source. So here I am connecting source to negative and drain to positive. So this is positive, this is negative. So as I am connecting negative at source terminal, the majority carriers in this particular N plus will be electrons. So because of this negative, the electrons which are present in N plus start moving from source to drain. So here electrons start moving from source to drain, because of which current will flow in the opposite direction, which is from drain to source. That's why we are calling this as IDS. Here this is called as VDS, this is called as VGS. So that's what I have mentioned here. Electrons are moving from source to drain, because of which current is flowing from drain to source. That's why we are calling it as IDS. So here I am taking VGS, which is on x-axis, IDS on y-axis. So this is called as threshold voltage. So whenever you are increasing VGS beyond the threshold voltage, then IDS will increase. When you increase VGS, this leads to increase in IDS, but when you decrease VGS below subthreshold voltage, the current does not vanish completely. It takes some amount of time for the transistor to turn off completely. So whenever you are reducing the potential below threshold voltage, it takes some amount of time. So this is called as some threshold voltage. So less than threshold voltage means this portion. So whenever you are reducing VGS below threshold voltage, it does not vanish completely. Why? Because it takes some amount of time to vanish completely. Why? Because some amount of electrons will be present in the channel, because of which there will be some amount of current called as subthreshold leakage current. So during this time, there exist electrons which are present in the channel between source and drain, which causes subthreshold leakage current. So whenever you are reducing VGS below threshold voltage, there will be some amount of electrons which will be present within the channel, because of which it leads to some amount of current called as subthreshold leakage current. This happens when the gate terminal is at static 1 or static 0, that is, which is below the threshold voltage. So this is about subthreshold leakage current. Now let us see some more points in detail about subthreshold leakage. The subthreshold leakage depends upon threshold voltage of the transistor. For example, higher the threshold voltage, lesser is the subthreshold leakage current. If threshold voltage is more, then obviously leakage current will be less. Note, if the threshold voltage of the transistor is more, then delay of the transistor increases. Why? Because it takes more amount of time for the switching. Lower the threshold voltage, higher the leakage current, but delay will be less. Why? Because it will be switching very fast. If threshold voltage is low, then switching will be faster. So obviously delay will reduce. So because transistor takes less amount of time to turn on. So that's why here delay will be less. Whereas higher the threshold voltage, lesser is the leakage current, but here the problem is delay will be more. Why? Because the transistor will take more amount of time to turn on. So this is the difference between lower threshold voltage and higher threshold voltage. Simply, if threshold voltage is less, the transistor will be switching very faster, but the problem here is we will be having higher leakage current. Whereas if you are going for higher threshold voltage, the transistor will take more amount of time to switch, therefore obviously delay will be more, but here there is no problem of leakage current, but switching will take more amount of time. So check this example here. I am taking some random VT1, this is the lower threshold voltage, some intermediate threshold voltage and higher threshold voltage. Because of these threshold voltages, we will get subthreshold current. So if you take VT1, here switching will be faster, but the problem here is leakage current will be more. This is higher threshold voltage. Here leakage current will be less, but the thing is the transistor will take more amount of time to turn on, because of which delay will increase. Whereas here delay will be less. Simply you can treat this as LVT, this is HVT, this is RVT or SVT, regular threshold voltage or standard threshold voltage. So that's what I've given here, lower threshold voltage versus higher threshold voltage. So VT1 is lower threshold voltage, VT3 is higher threshold voltage. So see here, when VGS is more, IDS will be more, but when you reduce VGS below threshold voltage, there exists some leakage current. Why? Because the transistor takes some amount of time to completely turn off. So it won't turn off immediately, because of which we get some amount of leakage current. But the advantage with smaller threshold voltage is that the transistor turns on quickly, so delay will be less. So for LVT, leakage current will be more, switching will be faster, and advantage is delay will be less. Now let us see for higher threshold voltage. When VGS is more, IDS will be more. Now when you try to reduce the VGS, that is when you come below the threshold voltage, the transistor turns off and there won't be much leakage current. The problem when threshold voltage is more is that it takes more amount of time for the transistor to turn on, so delay will be more. So this is about HVT. HVT leakage current will be less, switching will be slow and delay will be more. So we have to choose threshold voltage somewhere around VT2 to compensate these problems. So if you are going for lower threshold voltage, we are getting the advantage like delay will be less, but in HVT delay will be more. Suppose if you are focusing on leakage, then if you are going for LVT, here leakage current will be more, whereas here leakage current will be less. So you have to choose somewhere between regular threshold voltage or standard threshold voltage.